Good morning, everyone. This is the Transportation and Development Institute technical sessions. Welcome. My name is Carlos Negron. I'm the president of T&DI Dallas branch, and I'm happy to welcome all of you to our sessions. We'll be going in 1 hour blocks until we get to our main speaker at noon. Our first speaker is David Hutchinson. He is currently the Director of Engineering at Geoquest, formerly the Reinforced Earth Company. He has over 39 years of experience in the industry, specifically in the design of MSE walls. He manages over the technical issues for the company and has a vast array of experience as a structural and geotechnical engineer. He routinely consults on DOT and consults on the MSE wall technology. He serves as the principal expert on a T&DI International Committee on precast counterfeit walls, as well as a supporting expert for precast arches. He's a member of ASCE, the Geotech Institute, and several other societies. He's a graduate of Texas A&M University. Wait for whoop. Thank you. And graduated with a civil engineering degree in 1984. Help me welcome David.
Well, thank you all. Thank you, Carlos, for the invitation to be here and to present in the ASC Dallas branch technical session. It's an honor to be here. As Carlos already said, I just wanted to point out the logo at the top left is Geoquest, so formerly known as the Reinforced Earth Company. And this was a thing that happened about a year ago. I need to move something. Hang on. How do you move this out of the way? Anyways, it was a rebranding of Reinforced Earth because we have business units across the world that, so we changed to so where Geoquest is a name rebranding for all of our Reinforced Earth Company and across the world. So just wanted to clarify that. So thank you again, Carlos, for letting me come here. And when he asked me to present today, I was like, well, what can I do it on? So this topic here is traffic impact loading on barrier rails and how it affects MSE walls is something that I'm actually dealing with right now across the country. It's an important issue today. So moving forward here, just the agenda is here. It's kind of short, but a lot of stuff, a lot of meat in each one. And the first one is, if you would indulge me into doing a history of the development of roadside safety standards over the years and how this developed within America. And then from all that, we're going to look at how that helped develop the guidelines for design of roadway barrier systems.
Sorry? Speak closer to the microphone.
Okay. And how it helped develop the guidelines for design of roadway barrier systems placed on MSE walls. Then once we get through that, we'll look at the comparison of the current AASHTO, what it says, versus this new report that's coming out called the NCHRP 326 report, specifically for this topic. And at the end, we'll do some conclusions. So let me get into the development of roadway safety standards that has happened over the years. So as anything, so in the early 1900s, the birth of the automobile era happened. You had the development of the Model T by Henry Ford came out. Early automobiles shared the roads with the horse-drawn wagons, and safety standards were virtually non-existent. And as we went in and moved into, okay, sorry about that. I got to get used to this changing. So in the 1920s and 30s, rapid motorization led to increased fatalities. States beginning to forming highway departments to oversee their road design. Roadway safety was primitive. And this was the start of early efforts for standardization of our roadway safety. The Manual on Uniform Traffic Control Devices was first published in 1935. This was setting the national standards for road signs, signals, and markings, some other safety things. The introduction of the steel W-beam guardrail began in the late 1930s to prevent vehicles from running off a steep embankment is another development that happened in the 30s. As we move forward into the 1940s to the 50s, American built thousands of miles of new highways with more cars on the road, and they got a lot faster. So a lot more issues with fatalities that can happen. Basic roadway hardware guardrails and bridge rails became more common in the 1940s and 50s. In 1956, the Federal Aid Highway Act launched the Interstate Highway System. This entails the numbering of the roads from east to west was even, and north to south was the odd numbers. But it also triggered new safety engineering efforts. It also introduced consistent design standards managed by AASHTO, but later became AASHTO. In 1960s to the 70s, we had a rapid growth in the traffic, led to an increase in more fatality crashes. Cars got more congested on the highway, prompting serious safety research needs. In 1965, over 50,000 Americans were dying on traffic accidents each year, an alarming number that drew national attention. So in response to this, President Lyndon B. Johnson urged Congress to act. So Congress passed two major laws in 1966. One of them was the National Motor Vehicle Safety Act of 1966, which focused on the vehicle design itself. So the vehicles were mandatory. This is where you probably got airbags, stronger cars. They were concerned with the safety of the vehicle itself. The other act was the Highway Safety Act of 1966, focused on the safer roads, driver behavior, state highway safety programs. So these two laws were considered probably the most important laws passed in U.S. transportation history. Let me do one thing here. Okay, there. FHWA began setting standards for roadway hardware, such as guardrails, signposts, and breakaway supports. The development of crash testing procedures began, leading to performance-based design rather than trial and error. In the 1980s, the first major guideline for crash testing of roadway hardware came out in the NCHRP 230 report in 1981. It also introduced breakaway signs and light poles designed to shear off safely upon impact. Energy-absorbing barriers like sand barriers, crash cushions began to appear at high-risk areas. The focus shifted to forgiving roadsides, designing roads that reduce injury despite driver mistakes. The DHRP Report 350, which was setting the formal crash test standards for roadway safety devices. In 1993, this report, the NCHRP 350 was published in 1993. This report was the first major national standard that introduced what they call test levels, test level 3 to 5, for evaluating roadside safety hardware, including guardrails, barriers, terminals, and crash cushions. Each test level corresponded to a specific impact condition, such as the vehicle type. Was it a small car? Was it a truck? What is a small van, or was it a semi-tractor trailer? It also looked at the vehicle weight, the speed, and the impact angle that the car would hit the hardware. Oop. Okay, so, dadgummit. So the summary of the TL3 to TL5 from the NCHRP Report 350, and you can see the test levels here, TL3 to 5, the vehicle type, the weight of it, the speed that they specified, and the angle in which it would hit the barrier, and the typical use here. And in 2000s to 2020, they introduced what they called MASH, the Manual for Assessing Safety Hardware. Came out in 2009. It was an update in refining crash test procedures for modern vehicles. And they also introduced greater use of computer simulations through finite element modeling that was used to predict and prevent roadside hazards. So they also, besides the crash testing, they also started simulating and in a computer modeling. And AASHTO MASH 2009, when it came out, it was updated in 2016. So MASH replaced the NCHRP Report 350 as an official crash testing standard in the United States. FHWA began requiring MASH compliant hardware on any new or any replaced installation after 2006. So The final MASH update was released in 2016, so anything new after that had to meet the MASH requirements. 2018 to 2020, MASH retained the TL1 to TL6 test levels, structures, but updated the vehicle type and heavier pickups. So here's a MASH updated chart. You can see how larger it got from the NCHRP 350 report. You can see that some of the weights of the pickups, the vehicles got heavier, and the speed was about the same, but they introduced TL1 and 2, and they also have a TL6 now. You can see, thank you. You can also look at the typical use. So TL1 to 3 was typical for standard highway and interstates. TL4 was for urban expressways, busier roadways, and TL5 and 6 was for the high-risk areas where under bridges, hazardous cargo, and such. So these were defined typical usage. And just by the way, typically Geoquest does not specify the test level to be used on the barrier. This would come from the consulting firm designing it for the DOT. So look, the MASH crash test procedures is now used. So I said all that to get to this point and to say that this was used to help the guideline for the design of the roadway barrier system placed on MSE walls. So we're going to see a lot of cool stuff here. Got some crash tests. We'll see how they use that to develop the guideline. So let's look at, just a reminder for the audience, an MSE wall, what an MSE wall is. Some of you may not know, but it consists of a precast panel, reinforcing strips that's buried in the select backfill, and this comprises a mechanically stabilized earth retaining wall. Mechanically, MSE walls have been used since 1972 and across the United States on the highway infrastructure across the United States. An estimated 10 million square feet of MSE walls are used or constructed annually in the United States. So you can see how a lot of MSE walls are being used on our highway infrastructure. Okay, so based on the new guidelines, any roadway barrier system, and the barrier roadway system consists of the barrier itself, the coping, and the moment slab. So this is what the barrier rail system consists of. It needs to comply to the MASH defined test levels TL3 to TL5. Along with that, so let's look at how these test levels, TL3 to TL5, we'll look at that and the research that was done and how it affects an MSE wall. One of the major uses of MSE walls here across the United States is for bridge approach embankments. So you can see in the picture below, you can see an MSE wall is typically used up to a bridge structure, and that typically comes to be 25, 30 feet. You have an MSE wall, and typically it's constructed with the roadside barrier system on top of the wall, and that barrier wall needs to line up with the bridge rail on the bridge deck. So you see a lot of that. So the barrier system consists generally of a traffic barrier placed on a structural slab, a moment slab for flexible pavement. And you can just see here, here's a section of an MSE wall, and what I'm pointing to is a barrier rail, then the moment slab, and this is what the barrier rail system consists of on top of the wall. This is what we're going to look at. So understanding the behavior of the barrier system and the interaction with the MSE wall is very critical. As you can see here in the picture, this Miller light truck it did its job. It survived. It shouldn't have been over. It shouldn't have went over the barrier. Should it deflect it? But you can see here, it really took a big chunk out of the concrete barrier here. The cab was demolished, but luckily the beer was saved in the truck. So it's a good picture. That was from, I think that was in Fort Worth, over in Fort Worth. I'm not sure of the details about the driver, but it was an interesting picture that I thought I'd show. Now, through the years and through our work with Texas A&M University T&DI Center, one of the thing was I believe was misunderstood was that the dynamic impact design force, FT, in this chart right here, it was used to design the moment slab width. So in other words, the dynamic loads were being used to develop the size of the slab, which, and our taxpayers' dollars were being wasted. A lot of money spent on something that wasn't needed. So what happened was this spurred AASHTO in the cooperation with FHWA to start developing guidelines for design of roadway barrier systems placed on an MSE retaining wall. And it was under the National Cooperative Highway Research Program that they did it, the NCHRP. So this study was needed for several reasons. Number one, to come up with a more economical design for the barrier rail system with the moment slab with the different test levels, and to also look at how it affects an MSE wall. So, and this chart down here is the current impact. This is in the current AASHTO right now. So you can see they call it design forces, which is somewhat maybe misleading because that's really a dynamic load, because on the TL2, 3 and 4, it's a 54 kip load. And I'll show you later where the NCHRP increased that. Okay, so the NCHRP reports came out, and the final one is this report 326 on the right. But the earlier version in 2010 came out. It was called the report 663. And this was for the TL3 and 4, and then later they tested the TL5, and then the final report 326 came out. Now the people that was on this was we worked close with Dr. Roger Bly and Dr. Gina Luis Breo down at A&M, and this was the team that led this document to study it. And by the way, Geoquest, or Reinforced Earth, we were very involved from the very beginning. So you can see here, we had some acknowledgments in the report. Pete Anderson, our colleague from Boston, Carl Sanders, and myself were involved through all the studies that they did for the crash testing down at the T&DI Center in College Station. So the NCHRP 326 was a final report. This was dedicated to developing guidelines for the barrier moment slab system placed on MSE walls to resist vehicle impact loads resulting from the 3 test levels TL3 to TL5, and guidelines for the MSE wall. So this was what the whole purpose was, to size a moment slab and figure out what happens on the MSE wall structure. The recommendations provided guidance on dynamic loads applied on the traffic barrier for the following. Requirement for the barrier design. So the impact load hits the barrier first. So you have to design the barrier, and I'll show you some stuff. They use a yield line analysis on that. And then it came up with a static load equivalent on the dynamic loads used to calculate the moment slab width. This was the main thing I told you earlier. They want to try to reduce the moment slab size. So they came up with some equivalent loads, and I'll show you how they did that in a minute. Then also, the last was they came up with some pullout and yielding pressures that we needed to design the retaining wall for. The analysis performed include predictions of impact loads based on measured test data, really the crash test performance they did, crash test studies they did on a TL3 to TL5. And they also looked at finite element impact analysis simulations. So not only did they have the crash test, but they also had simulations in a finite element model used to look at the different load conditions there. So let's look at, let me see, is it coming up? Okay, so I just threw this picture in here because I thought it was cool. It showed you kind of the size of a small truck and pickup. You can see the small unit truck, and then you can eventually see the tractor trailer here. You can see graphically the moment slabs are about relative to the size they came up with. The TL3 was about 4 foot wide. The TL4 is 4.5. And on the TL5, the moment slab ended up being 12 foot wide. And I'll show you some results and how they got to that here in a minute. But meanwhile, let's look at some video. So this was the TL4 impact crash test. This was done down at T&DI Center. They had an old runway where they converted into where they crash tested. And T&DI was very famous for crash testing the hardware, safety hardware, to meet the match criteria. So what happened was, back in the early mid 2000s, Geoquest we got involved. You can see the MSE wall down below here. This was a cruciform panel. It was highly instrumented, and you can see, I'm going to give a preface. You can see this truck doesn't have a motor. It's being pulled by a cable. The pulley is right there on the ground. So this cable is pulling this way, and another truck is pulling it to the left on the screen here, and it's getting it up to the 62 miles an hour. And here is the crash test. Watch, the front end's going to hit it. Then the second load, the back end of the truck swings around and hits it again. And that's another big load that happens. some cool video. That's a TL4. Here's another side view of it. So they're measuring all this, and they're measuring the dynamic load that hit the barrier on that. Now here's the Big Daddy. Oh, wait a minute. Yeah, no, that's it. So this is the TL5 impact loading. You can't see the retaining wall, but the barrier is on top, and they have an instrumented retaining wall below it, and they're also instrumenting the barrier for movement and deflections and what's happening there. So what I'm saying is the T&DI Center was very precise. They knew what they were doing. They had instrumentation. They had strain gauges everywhere. And so when they wrote the report, it was very detailed. This report was, I think, 400 pages long. So from all that, from all the crash testing, you can see here some pictures. We have real crash testing shown on the left. I'm sorry, I didn't have the TL3 truck one. I couldn't find it, but you can see how they did crash testing on the left, and then on the right, they had the simulation that they used in the finite element study. So from that, you can see the peak dynamic force here. You can see the graph. You can see the initial hit for the TL3 load was highest at the initial hit, and then the back end of the truck swung around, and you had a higher load hit there. So that's what that is. So this is the front, and then this is the back of the truck. So the maximum dynamic force was determined both for the crash tests and for the simulations. This chart here, it was in the report. It's table 9.6. It's a summary of the crash test, barrier, and the simulations displacement results. So this whole test was a function of how much it displaced. So this was kind of the guiding thing. So, but the thing to look at here was that not all the tests were crash tested. A lot of them were simulations in the model. So what they did was, when they set the finite element model up, they calibrated it from the crash test to get it close to as possible. So you can do a lot of manipulations with the simulations, with the computer program, because when you do a crash test, it's not cheap. So this is the way they did it, and you can see what they did. So here, that there. So for example, the TL 5.2, you can see the loads that they got from this one was all based on the computer modeling simulations. It wasn't from crash testing. The objective was to determine a moment slab width that resulted in a maximum permanent deformation of the coping. So you can see here in the very far right column, the coping, and you can see that they said, okay, what is the minimum moment slab width to keep the deflection down? So for the TL3, they had a 4 foot. This was the minimum moment slab width. It's in the report. This is the minimum width of 4 foot. You can see a 0.63 inch deformation of the coping. So that was good. For the TL4, they had a 4.5 foot moment slab width minimum, 0.79. And then we got the 7 foot and a 12 foot for the TL 5.1 and 5.2. One thing to notice is that you can see here in the line, right? For the TL3, for example, the crash test and the simulations, you can see it's side by side. So you can see the deformations of the crash test was 0.25, but yet for the simulations, 0.71. So that tells me that the simulations that they did were a little bit conservative, on the conservative side, to simulate the model. So one thing that I was telling you was that they developed the dynamic loads from the crash testing. And this dynamic load, the new one, LD, is used for the barrier design. So when you design the barrier, they use a yield line analysis in chapter, it's in AASHTO. You can see the new loads here. For the TL3 and the TL41 is 70 kips. TL42 is 80, and then 160 and 260. But these loads were calculated based on crash testing and the simulations that they were getting. So that's one thing that they developed in the study. The other thing was the static load equivalence to the dynamic loads. I can show you that the equivalent static load LS was developed from the dynamic loads from table 9.1. So you can see here the LS, this was the equivalent static loads that they developed from that. The equivalent static load is used to determine the size of the moment slab. The recommended moment slab width is W min. And the way they determined that is we knew what the structure was based on the real crash testing. They knew the structure, they knew the size of the moment, the barrier, they knew the dynamic load, and from what they did was they just back calculated what the equivalent capacity demand ratio of the barrier system, and they've got the equivalent load that way. That's how they determine the equivalent static load. The 9.1 also provides a minimum length for a precast full barrier. Sometimes we precast a full barrier, and if you want to do a TL3 to TL4, then it needs to be a 10-foot minimum width. And then when you get into T5, 1, and 2, you need to have a 15-foot long precast full barrier. And sometimes people do that, like up in the north regions where you have people, the labor shortage, they like to precast a barrier and you don't have to flip form it that they do down here, but that's an option that is in other states. Let's look at the calculation of the pullout and the yielding pressures that were developed from the crash testing. So let's look at the load pass. So the load pass is, first of all, it hits the top of the barrier as shown here in the red. The load pass goes to the barrier and down into the coping and into the moment slab. And then from the moment slab, it's a vertical pressure into the soil. So the vertical pressure into the soil is a vertical load. Then you multiply that times the coefficient of lateral earth pressure, and you can get the loads that transfer into the strips. That's just a cool picture I added in there. Only the top 2 strip levels were tested. So in the report, they only monitored the top 2 strip levels, as shown here in red over here on the left. Strain gauges were placed on the metallic strips to measure the dynamic loads and the loads and what was happening in the loads being transferred into the strip. In the wall reinforcement design, there's 2 modes of failure. Number 1 is it can pull out of the soil just from the reaction, and it also can yield the steel. So these are the 2 things that we are concerned with, and these are the 2 things that they developed the pressures for. So here's a pressure diagram that came from the NCHRP 326 report. This was a design pressures for the reinforcement pullout and the tributary heights. You can see here in the red that the top strip obviously gets more load. So the load is higher, about 1.24 KSF pressure down to 3, depends on the test level they're testing. Then the second level is a lot lower, as you can see here. So if this report is used in the design, then we would check our bond pullout for these pressures. Going to the design pressures for the reinforcement yield, this means that we check this against the steel yielding or rupturing. And you can see for the TL 5.2, it's a huge load of 4.44 KSF pressure at the top of the panel. And then the lower ones are a little bit lower. So this is what we have to design for if it's specified. This is not approved in AASHTO yet. So let's compare the current AASHTO to the NCHRP report. The current AASHTO, let's look at current AASHTO. So this is the current AASHTO forces in the current AASHTO here. And the difference is that the dynamic loads is referred to design forces. So that's one difference that could be confusing. Design forces. The AASHTO dynamic loads are significantly less than the NCHRP report. I'll show you in a minute on that. There are more test levels in the AASHTO. They have a TL 1, 2, and 6 now. And this is the function of the speed and the height of the rail. There's more information provided in the AASHTO than the NCHRP, such as the longitudinal and vertical loads shown right here. And they also define LT and LL, which is the length of the impact load across the barrier. This is the NCHRP 326 dynamic loads. You can see here that the NCHRP dynamic loads are more or higher than the AASHTO loads. So the typical one we saw was 54 kips, and now the NCHRP is reporting them to be 70 kips, and then 160 for the TL 5.1. They didn't define these other ones, but this is how it compares. So you can see the new report has a higher impact dynamic load requirement for the barrier. And I'm not saying to use it, I'm just saying this is what's reported. And this has not been approved by AASHTO yet. So in your designs, this is what is in the report, and you can choose which one to use. Okay, we've already talked about, yeah, I mean, so the NCHRP report also have intermediate levels. So the AASHTO only has TL4. Now the NCHRP has a 4.1 and 4.2, so forth and so on. The minimum moment slab length for the barriers also in the report here. Already talked about that. And I already said that this report is not in AASHTO yet, hadn't been approved by AASHTO yet. The reinforcement traffic pullout for in AASHTO, the current AASHTO criteria says that for you use a 10 kip load divided over 20 foot. Basically, you get a 0.5 kips per foot in that loading, and then you have to apply it. I'll show you in a minute the chart, but you have to distribute it according to this chart. For the yielding, it says to design 10 kip load over 5 foot, which yields about 2 kips per foot on the strip design. And again, it's applied according to the figure right here. So the way they do the loading is they take the load, they say distribute it triangularly on it, and we can calculate the pressure on top of the wall here. This is the distribution. This is the average pullout value here is 0.094 KSF. This is the distribution. This is the AASHTO standard now. The average yield is 0.37 and 0.27 accordingly there. When you look at the NCHRP report 326, you can see the huge difference when you have to design for this. So for the pullout, you go from 0.37 KSF to 1.24 on the top strip versus 0.094. So this is a really dramatic increase. So this reporting is a dramatic impact on the MSE wall design. The second level is not as bad, but if you look at yield, it goes from 1.4 all the way to 4.4 KSF versus on the AASHTO way, you're looking at 0.37 KSF versus a 4.4 potentially. So very big difference in the loadeds here. The conclusions is it's not adopted in AASHTO, and I'm not saying to use this. I'm just saying it's not in AASHTO. So the consultants that specify this can specify it according to your DOT. They may want you to use AASHTO, or they may say you need to implement the NCHRP 326. We've seen it both ways across the United States. We've seen DOTs want you to design the wall according to the NCHRP 326. And so we've seen a lot of misunderstanding, miscommunications, and it's not well thought out yet. So the dynamic loads have increased from the barrier design, where you talked about that. The static load equivalents now will yield some reasonable economical moment slabs. The pullout and yielding pressures have been provided to design the top two levels. The loads have tremendously increased from the current AASHTO. The new loads will significantly increase the design of the soil reinforcements if we have to design for that. Now, keep in mind this: the recommendations of NCHRP report was based on the testing of metallic reinforcing strips of an MSE wall. And what I've seen across the United States is a lot of people want to go, okay, you have this other different wall type. Say we have a tech wall, which is a precast counterforted wall system. We have a T wall, which is a precast stem T. It's like a modular wall. And they specified that we apply these loads to these type of walls. And this is where we disagree, because we think that this is a misappropriate way of using it. So caution should be used when extrapolating these results for the design of other type of wall systems. What was tested was metallic reinforcing strips. They should be used for an MSE wall. When they try to use it for these kind of walls, I think it could be either underestimated or overestimated. We don't know, but they need to study this kind of wall. So this is what we're seeing across the board, across the United States, is people are specifying it, and it's not being done correctly, I don't believe. The walls have a different behavior. The walls could be stiffer, they could deflect more. We just need to study it. That's it. Any questions? I know that was kind of quick.
Questions?
Yeah. Yeah. TxDOT right now is the current AASHTO standard. TxDOT, and if you look at their rail sheets, it says it's been in compliance with MASH TL4. TxDOT doesn't apply any, well, in the past, they haven't been, TxDOT does not enforce that you follow all of AASHTO. So we haven't been using even the AASHTO criteria for the strip design. We haven't even been using that. I don't know what they're going to do. I know they came out with LRFD, so I'm not sure if they will look at this or not. I don't think the DOTs are fully accepting this report as a guidance. I think it's a report done by the T&DI Center and the PhDs that did the research. You can download this report and look at it. There's all these guidelines that are there. So I think each state would have to decide if they want to introduce it into their work. Yes.
Selfishly asking this, so I know to just repeat the last little bit, the last 2 minutes of your presentation, you said this is not being applied right. Can you just, because that got my antenna up, and I want to be sure I'm understanding what it is you were just saying.
I think, okay, thank you for the question. I think for the MSE wall design, it's applied correctly. I mean, the guidance is clear in the report. It's for MSE wall with metallic strips. What I meant was that some of the DOTs want you to use this NCHRP 326 loading, which I showed you is 4.4 KSF at the top over 1.6, and apply it to another type of wall system that's not an MSE wall. That's what I meant, because that's what we're seeing. I'm dealing with it right now in another state, won't name state names, but they're asking us to design it, and I'm going, this doesn't seem correct. Then we're also seeing that, okay, remember I told you that the barrier wall system needs to be designed for the guidelines, and we're not totally sure, but it looks like it's a little weak on meeting what they designed, is in the report, meaning that they need to bury a MoMA slab 3 feet in the ground and come out 12 foot. We're seeing at-grade MoMA slabs, and they're saying we need to design for a 5.2 impact loading, which seems to be an at-grade MoMA slab's way different than an embedded one. So that's what I meant by that.
Thank you.
Any other questions? Carlos, I know you have one.
Well, I do have one, but I was going to wait for Michael to get up here. Okay. So to David's point, several of us are working on projects throughout the country, right? Design builds. This is a relevant topic when it comes to those type of projects, because they are, in the case of design build, it's a fast paced. They want to use, the DOTs usually specify the latest technologies or the latest requirements or the latest research that's coming out of T&DI. And I mean, I personally think it's great that Reinforced Earth, Geoquest, you, David, were involved in the specific research that was occurring there, because to go from research to implementation usually takes time. When we have the people on the ground who are dealing with this, who are sending us the shop drawings that are needed to construct those projects, to get them into the ground as quickly as we can while the research is occurring at the same time. That's a lot quicker than how things used to be, where you'd have the research, it would go through committees, it would go through, and again, David has said, this hasn't been adopted by AASHTO. This is not being implemented countrywide. In fact, you also mentioned that TxDOT, and maybe some may have missed this, is that they haven't adopted LRFD, right? So different states have adopted different stances on retaining walls, right? If you look at Nevada, California, other states, naming states, they have adopted LRFD, and they erroneously use the dynamic loading that he mentioned, the 54 kips, for example, to design moment slabs, which is what he's saying. That's a dynamic load. That's not a design load. It's erroneously mentioned in the AASHTO Chapter 13 as a design load when it's actually a dynamic load, right? So there's a lot of commentary, and I'm going through this on my own projects, where you have to read the commentary and understand the difference between what is a dynamic load, what is a design load, which one do you design for, right? Do you design this one for, I think we had this conversation last week. Do you use this specific load for
for stability and this other one for reinforcing, you know, and there's just a lot of misunderstanding of how to use the information that's in AASHTO, right? As engineers, we have to look at the code.
Yeah.
We have to interpret it. I have my discussions with David. In fact, David and I have known each other now almost 15 years. I come to him as a resource. I've got him on speed dial. I encourage each one of you to get him on speed dial, because when you have questions like this, when you're reviewing his shop drawings, when you want to get those things in the grounds quicker, there's no better way than picking up a phone. And yeah, you know, some owners get a little bit squirrely about that, but at the end of the day, they want their projects in the ground. We want to make sure we're on the same page as the folks who are putting it in the ground. So I highly encourage everyone to do that. We are wrapping up this first presentation. We want to thank David Hutchinson for his great presentation. Apologies for the earlier, the late start and some of the tech issues. We're getting them cleaned up as we go. I want to thank everybody for coming. Let's give David a round of applause.
Thank you.